All right. Reversible reactions in equilibrium. The start is pretty basic and something back from IGCSE. Okay. So we know that reversible reactions can be reversed. They may go into forward direction as well as in backward direction, maybe both of this simultaneously. For example, the book says it gives you the example of the blue hydrated copper to sulfate. When that's heated, it loses water. This is the dehydration reaction for it. We form the white anhydrous copper to sulfate. Along with that, we produce water. This is the forward reaction. Now, the reaction can be reversed if the water is added back to the anhydrous white copper to sulfate, and it is going to form the blue salt. Now, when these reactions are written with the fresh hook arrows, we call them the reversible reactions, which is dehydration as the forward reaction and hydration as the reverse reaction. A reaction in which products can react to reform the original reactants is known as a reversible reaction. In this case, heating and adding water are not being carried out at the same time. However, there is a type of chemical reaction in which forward and backward reaction may take place at the same time, as I've said earlier. Now, in many chemical reactions, reactants are not completely used up. Some of the products are formed, but the maximum theoretical yield is not obtained. That actually goes for many of the reactions. A mixture of products and reactants is formed. Products can react together to reform reactants at the same time as reactants are reacting to form products. So this type of reversible reaction is known as an equilibrium reaction, and we specifically call it an equilibrium state when the rate of the forward reaction and the rate of the reverse reaction are equal. For example, let's consider the reaction between hydrogen gas and iodine gas, and they are carried out in a sealed glass tube at 400 degrees centigrade. That's why iodine is in the gaseous form. Molecules of hydrogen iodide will be produced, but at the same time, the reverse reaction would start happening in the form of a hydrogen iodide, breaking down or decomposing to form hydrogen and iodine, and that happening at the same rate as hydrogen and iodine are reacting to form hydrogen iodide. Now, a simple diagram has been given to give you the idea that how the reaction mixture would look like, and it does tell you that the reaction mixture would look like a mixture of reactants and products both. Now, when fizzy drinks are made, carbon dioxide is dissolved in drink under pressure. When you take a lid off of a bottle of fizzy drink, bubbles of carbon dioxide suddenly appear. Carbon dioxide is actually released from the water. When you put the lid back on, the bubbles stop. This is because of the equilibrium reaction. Now, carbon dioxide in the form of gas is being converted into carbon dioxide aqueous. This is a very good way to show it. Now, forward reaction happens during manufacturing and backward reaction happens during opening. We do understand about this, but there are some specific characteristics of an equilibrium we need to study. Now, an equilibrium reaction has particularly four features under constant conditions. Number one, it is dynamic. When I use the word dynamic, it specifically means that the forward reaction and the reverse reaction never stop. The other kind of equilibrium is equilibrium at rest. We also call it static equilibrium. Static equilibrium may exist in physics, but it does not exist in chemistry, in chemical reactions. Now, in chemical reactions, we can't say really that the reactants will not react to form products and the products will not react to form reactants. That actually does not happen. We call it dynamic because the system keeps on moving in both directions at the same time with the same rate. And that actually is the second point, which is, I think, pre-explanatory since we already know that forward and reverse reactions occur at the same rate. Now, concentration of reactants and concentration of products remain constant at that equilibrium. Okay, this is because the reactions are occurring at the same rate. Now, it requires a closed system for this to happen. If the system's open, most of the time, what happens is the gases can leave the system. Once any mass, any form of mass can leave the system, the characteristic of equilibrium that we give first, the first three ones, we won't be able to achieve that. The rates won't be the same. The amounts will not be the constant. I mean, I'm talking about the concentrations. And of course, dynamics may go on, but at one point, dynamics would simply convert into one kind of reaction, the one that can really dominate. So a closed system is required in order to actually exhibit or experience the first three characteristics. The book is going to do the same. It is going to explain all of this. The dynamic means that the reactants and products could keep continuously reacting or changing into one another. Forward and backward reactions occurring at the same rate means the number of molecules or ions of the reactant forming products, the same one would be in terms of products breaking down into ions. Now, it's important we can get to equilibrium state by starting from only the reactants or only the products. At equilibrium, the concentration of products and reactants is constant, does not change since both the reactions are occurring at the same rate. Lastly, in equilibrium, molecules of reactants are reacting to form molecules of products at the same rate as molecules of products are reacting to form molecules of reactants. It means pretty much the same thing, that the rate of reaction for forward and reverse reaction is going to be equal. Now, the concentration of reactants and products remain constant at equilibrium. This is something that we can understand from the rates of forward and backward reaction. Of course, when they are equal, equilibrium can be approached from both directions. And in that case, what's going to happen is that the amount of hydrogen and iodine being reacted to form hydrogen iodide would exactly be equal to the rate of hydrogen iodide being broken down to give these two at the same time. So the react concentration remains the same. Now we can start by either mixing of colorless hydrogen gas and purple iodine vapor. We can start with only colorless hydrogen iodide gas. So you can start either way. You can either move from forward to reverse or from reverse to forward direction. Now, our figure shows that what happens when 5 into 10 raised to the power 3 minus 3 moles of hydrogen, same moles of iodine, react at 500 Kelvin in a vessel of volume 1 decimeter cube. When the time passes, purple color of iodine fades until equilibrium is reached, which means iodine is currently reacting with hydrogen. At the equilibrium mixture, it contains 0.68 into 10 raised to the power minus 3 moles of iodine, and that's the same of hydrogen. However, 8.64 into 10 raised to the power minus 3 moles of hydrogen iodide. These kind of values are going to give us certain answers to our questions, and I'm going to specifically discuss that, what that means. Now, let's take a look at this graph we have been using previously in IGCSE. We haven't been exactly using this double graph at the same time in IGCSE. We have just been using the graph for products. Since this is a multi-graph, it contains the graph for reactants as well as the graph for products. Now let's take a look at the graph. There are two curves in this graph, and one of them is showing as an increased line and the other one as a decreased line. Let's talk about them one by one. Let's start with the increased line, this one first. Now this line shows the increase in the concentration of hydrogen iodide. Definitely it's the product graph. And as the equilibrium is established, the equilibrium slowly establishes, there comes a point when equilibrium establishes, and from there onward, this line stays constant. So there was an increase in concentration of hydrogen iodide until equilibrium is reached. When the equilibrium reached, the concentration stays the same, so the line stays constant. On the other hand, we have another graph, a line that shows decrease. This is the concentration of both hydrogen and iodine since we took equimolar amounts. And as the equilibrium is established, this line also becomes constant. You put an arrow over here, you can put a same arrow over at this point, and actually it would be here, not over here. So this gives us the idea that for product, the graph increases because the amount of product increases, and then it becomes constant. And if we talk about reactants, for reactants, the graph decreases and then becomes constant. So decreasing trend graph is the reactant graph, and increasing trend graph is the product graph. So we do get an idea that product and reactant graphs are actually the exact opposite to one another. And that's because the amount of product is increasing and the amount of reactant is decreasing because of the reaction. Now the changes in concentration of reagents as 5 into 10 raised to the power minus 3 moles of each of hydrogen and iodine react. So we started off with what? We started off with 5. The lines have been drawn to a very specific set of points. Since both of them are hydrogen and iodine start from 5, so the line starts for 5. And this line represents either hydrogen or iodine. And since both of them at equilibrium have a very specific concentration, so the line ends at that concentration. In the case for the reactions in which there is no product present at the start, product line obviously always starts from 0. And then if in this specific case, it reaches to a point of 8.64 in 10 raised to the power minus 3. Why do you think it's 8.64? Why are we being so specific? Any idea? Come on, it's simple mathematics. Try to think about it.
What do you say again?
Why do you think it's 8.64 and not any other value? I'm just trying to ask a question about numbers. Do you think the numbers that we're getting on the right hand side of the graph, 8.64 and 0.68, do you think they mean anything? Do you think we have these numbers for a reason? Or can you think of the reason? Anything in mind? Come on, wild guesses. If not anything, and if you can't come up with anything, say it out loud, that's fine. If you think your guess might be embarrassing, you can always write it in chat. Remember, these numbers have a very specific meaning. And these numbers can always be correlated into with one another.
No matter, maybe it's no matter with which amount of reactants we start, it will always end up to these numbers.
And why do you think we'll end up with these numbers? Always is
Yeah,
not
like
the right word over here, but yeah, you're close. And that's one way of perceiving it. I'm just asking you to play with numbers, not with the theory. Do these numbers mean anything? Do they add up to something? Do they subtract to something? Okay, let me clarify. Now, the concentration of regions, and there are two regions, hydrogen, which is 5 into 10 raised to the power minus 3 moles, okay, and iodine, which is also 5 into 10 raised to the power minus 3 moles. I hope you understand we can write it like this, or I can simply write it like this, which means this and this are the values. Okay, what do we end up with? Since we have both of them, we end up with 10 into 10 raised to the power minus 3. Okay, right? That's why this graph was as high as 10. There is a very good purpose of putting all the numbers over here, whatever those numbers are. Now, understand, this is the total amount. And since we have already studied the law of conservation of mass, and we already know that we cannot create or destroy mass during a chemical reaction, and it actually stays the same, stays constant. So we do understand that we can always discuss these numbers and equate them equal to this. Now, since we have hydrogen at the end of the reaction equal to 0.68 into 10 raised to power minus 3, and we have the same concentration for iodine at the end, or we may say at equilibrium, what does that equate to? 8 and 8, 6, and this is 0.136, right? Sorry, 1.36. You must be thinking, what am I doing? I was thinking 1.36, but I wrote 0.136, right? Okay. And the product that we have made has the concentration of 8.64 into 10 raised to power 3. What do you think that adds up to? Right?
Yeah.
So there is a reason of why we have drawn the graph like this. As soon as you see the graph, you can always look up the numbers, you can always work them out, and you'll get to know that the starting line or the ending line for any line has a specific purpose. So the reactant starts from 5 because that depicts the amount they start from. The reactants end at 0.68. I'm going to discuss why they end at 0.68. The products start at 0 because there were no products at the start of the reaction, but they increased to a specific equilibrium that was 8.64. Yeah, we do understand that if we add 8.64 and 0.68 two times for hydrogen and for iodine respectively, we end up with the same value of 10 into 10, 10 multiplied by 10 raised to power minus 3 moles that we started off with, proving the law of conservation of mass. But there is another point to it. Out of 10, the total amount, the product reached 8.64. So if we take this 8.64 and we divide it by 10, and since both the amounts are minus 3, so I'm not really going to consider it, that means this was our percentage yield. Not that we end up at this yield every single time. Of course, yield can be increased or decreased based upon factors that we have previously discussed. It may never decrease in the theoretical yield, but of course, actual yield can be changed with the help of changing a few factors. That's what this whole thing means. That's how we connect it to our previous knowledge. So far, whatever we are doing is something that we have discussed previously. Percentage yield is something that we have done in the past in IGCSE, right? And law of conservation of mass is also something that we have studied back in IGCSE. We also know that for any reaction, if the product is not present as a part of the system at the start of the reaction, the amount of product is always zero, right? So I hope you do understand all the numbers here or any graph. Whenever you look at a graph, just I usually tend to ask my students, never look at the graph dumbfolded. That's not the way to look at them. You can always look at them in such a way that your eyes are filtering the numbers and the words into the useful figures or the useful data that you can actually use for any theoretical or maybe any quantitative questions. I hope I make many points clear at the same time when I discuss why the numbers at this graph really lie at the point they are. I hope I have made my point clear, right?
Yeah.
Good, good. Okay. So whenever you are going to look at the graphs from this chapter, try to look at them in such a way that you are filtering the whole pieces of information out that are useful for you. Okay. Now, not to forget, this entire reaction was carried out in a vessel of volume 1 decimeter cube. also a part of information that was given to us. Now, figure 8.5 shows the same equilibrium that can be achieved when 10 mole of 10 into 10 raised to power minus 3 mole of hydrogen iodide molecules decompose to iodine and hydrogen. And if we start up from that point, so we can go for the same amount. So whether we draw the graph like this or we draw the graph like this, it's just a way of perceiving it. I hope you understand that this kind of graph is a left to right equation graph, right? Which means we always start from the left hand side. We show the values on the left. We start off the values on the left for reactants and products, and we go all the way to wherever this whole thing should go. Okay. Because at the left of the equation told us there are 5 in 10 raised to power minus 3 moles of both hydrogen and iodine present, and there was 0 moles of product present at the start of the reaction. Now, this graph is somewhat a similar graph, but this is actually a right to left graph. Okay, right to left for the equation. Now, the right part of the equation actually discussed that there were probability for 10 mole per 10 into 10 raised to power minus 3 moles of HI, theoretically speaking, but that was actually never made because HI was able to decompose into hydrogen and iodine. So some of the hydrogen and HI decomposed, and the amount was brought down to this. And that decomposed amount actually produced some hydrogen and some iodine for us, which actually turned out to be this. So it's a way of perception. It's a way of discussing reactant to products or product to reactant type of the whole graph. Okay. So don't worry. Either way, the question can be asked or the answer can be answered. So whether you go with the direct argument or whether you go with reverse argument in a chapter like this, they're actually equally important. And that's why Cambridge gives you marks for both if they're correct. So moving on. One very important point that equilibrium requires a closed system. Now, closed system is the one in which none of the reactants and products can escape from the reaction mixture. In open systems, the matter is lost to the surroundings. For example, the gases may be released to the surrounding. Figure 8.6 is going to show us the difference between cold closed system and open system when calcium carbonate is heated at high temperature in a strong container. An example we studied back in IGCSE. This example was the very end of chapter 7 of IGCSE book, where you discuss the same thing: rate of reaction, speed of reaction, equilibrium. You discussed all of that back in chapter number 7 in IGCSE. The last page discussed the same example: calcium carbonate being thermally decomposed into calcium oxide and carbon dioxide. Now, many chemical reactions can be studied without placing them in closed containers. They can reach equilibrium in open flask if the reaction takes place entirely in solution or no gas is lost. So in that kind of reactions, we feel ourselves safe and we don't exactly require closed containers. But in the case of a reaction which is producing a gas or using a gas, in a closed container is actually inevitable. Okay, so if you take a look at this, calcium carbonate is being decomposed into calcium oxide and carbon dioxide, and since they have shown all three kinds of particles, you will easily be able to see that in B part of the diagram, in open system, carbon dioxide is the one that can easily escape since it's a gas. And once the gas escapes, this reaction is not a reversible reaction anymore. Take a look at the equation. If you ponder about the center part of the equation, you would notice there is an irreversible arrow. Why? This reaction will not be able to be reversed in the way that equilibrium does. And in this specific one, we have a reversible arrow. We do understand that this reaction is not just reversible. In fact, the rate can become same too. Once they do, an equilibrium will be established. And once an equilibrium is established, really the concentration of the all the species in the system will not change. And that's what's the best part about a closed system is. We can actually go with equilibriums. So it's pretty simple. Closed system can be defined as a system in which cannot lose any reactants or products or their parts. Okay, so let's move on. Changing the position of equilibrium. Something that I usually do with my students in a very good detail back in IGCSE, so much so that you don't have to do anything extra at A level. But still, we're going to discuss every point that we had back in IGCSE and whatever step up is there. And there are very small and slight step ups in A levels. So anyone who had a good grasp on chapter number 7 back in IGCSE is really going to love this part, since this part is going to be actually a skim through of the same kind of information. So some important parts. Number one, remember that although the concentration of reactants and products are constant at equilibrium, this does not mean they're equal to one another. And that is the most common mistake that students make. When we say that their equilibrium concentration is constant, they try to take the meaning out of it is that they're equal. They try to start considering that the concentration for reactants is equal to the concentration of product. Now, this is not what we meant. This is not true. We're just saying whatever the concentration of the reactant and the product are, it would stay constant at equilibrium. Now, if you remember the reaction that we previously picked, I am going to take the same example of hydrogen and iodine reacting to form hydrogen iodide. I hope for the products for hydrogen iodide, you remember the numbers were 8.64 into 10 raised to power minus 3. And for the reactants, each one of them was equal to 0.68 into 10 raised to power minus 3. Now, they are not equal to one another, though they would stay constant for the time the equilibrium has been attained and stays there in the same form and is not disturbed. Until unless the equilibrium is not disturbed, the products, the concentrations will remain constant. Constant. The word is constant, not equal. The second one, the position of equilibrium tells us how far the reaction goes to product or reactant. So the position towards the right hand side, the position towards the left hand side gives us a very good idea whether it's going to favor the products or it's going to favor reactants. You have been practicing the same thing back in IGCSE. Point number three, if the concentration of products is greater than the concentration of reactants, what we usually say is that the position of equilibrium is to the right, which means the product side, which means the amount of maybe the concentration of products is definitely greater than that of reactants, which is already mentioned as the starting part of this sentence. Moving on to four, it's actually the vice versa. If the concentration of products is far less than that of reactants, we say that the position of equilibrium is to the left, which is the reactant side, which means the concentration of reactants is much more than the concentration of product, which means the reaction has proceeded for in the forward direction of very little. Since for the former one, it moved to the product side a lot, and in the latter, it didn't. Let's come to point number 5. Remember that for equilibrium reactions, you always have to refer to the equation written. If you write it the other way around, the reactant becomes the products becomes the reactants. Vice versa is actually true. So this means you always go with the equation that you're given and you do not try to change it. If you try to change it and then you try to explain it, you're actually going to ruin everything, because you might be writing the not the required stuff, but exactly the opposite. So let's discuss the position of equilibrium and about changing it. And remember, whatever factors you studied back in IGCSE, the Le-Chatelier principle, everything is going to be the same. The position of equilibrium refers to the relative amount of products and reactants. Remember, relative amount, not the absolute amounts, the relative amounts. So the relative amount here of products can be more than that of reactants if the reaction or position of equilibrium is too far on the right. Vice versa, the relative amount of reactants can be much more if the position of equilibrium is too far on the left. So, if a system is in equilibrium and the equilibrium is disturbed, let's say by a change in temperature or pressure or any other stuff, the concentration of products increases relative to the reactants, we say the equilibrium has shifted to the right. That's how we express it. And I hope you already understand the method since you have done the same thing back in IGCSE. Now, if the concentration of products decreases relative to the reactants, we say the opposite. Position of equilibrium has shifted to the left. And this whole idea was very much given by Le Chatelier's principle. Now, changes in both concentration and temperature affect the position of equilibrium. When any of the reactants and products are gases, changing in pressure may also affect the position of equilibrium, just like concentration did. For French chemist Le Chatelier observed how these factors affect the position of equilibrium. He put forward a general rule, which we call as Le Chatelier principle. Now, if one or more factors that affect the dynamic equilibrium is changed or are changed, the position of equilibrium moves to minimize this change, actually to negate that change. And this is a simple line. This is not a complete principle or a definition. So if you look at the complete principle or definition, you're going to find in the reference books or even in this book's glossary the phrase as much as it can. So the change is tried to be minimized as much as possible. We can predict the effect of changing concentration or pressure or temperature, referring to the stoichiometric equation of the reaction. We can predict the effect of changing the temperature by referring to the enthalpy change of the reaction. So if we know the exact things about the reaction, we can always predict the effect of changing the condition. So how does change in concentration affect the position of equilibrium? Okay. So when the concentration of one or more reactants, and in this specific case, is increased, the system no longer stays in equilibrium. The equilibrium has been disturbed, and a new equilibrium is supposed to be attained. So that way, the position of equilibrium moves to the right to reduce the effect of increasing concentration of reactant. More products are formed until equilibrium is restored. So now we know. It's something that I also explained back in IGCSE. And I usually come up with the funny words. Actually, I say as per the Lee Chatelier principle, but he's trying to tell us is that a dynamic equilibrium is like a naughty child. He never does whatever you ask him to. Actually, he tries to do the exact opposite of what you ask from him. Just like a naughty child, sometimes you want to discipline him, sometimes you want him to be quiet. Sometimes you want him to be a little bit attained at a single position, not to be so restless. But every time you ask him to do something, he does the exact opposite. You ask him to rest, he doesn't. You ask him to be quiet, he doesn't. And Lee Chatelier principle says almost the same about a dynamic equilibrium. So the position of equilibrium will move to the right, and that is to actually reduce the effect, to actually oppose the change and to oppose the change as much as possible. So the amount of change you made, remember, the opposition would very much be likewise. For example, if you wanted to change the concentration of one or more reactants, and if you wanted to increase them, like the scenario says, you increase the concentration of a reactant by a pinch, the opposition would be just enough for a pinch. If you actually increased it by half a kilo or something like that, that is really a big change. So expect the opposition to be the same, right? So moving on, when the concentration of one or more products is increased, the system is no longer in equilibrium. Again, the position of equilibrium moves towards the left to reduce the effect of increasing concentration of products. So what it tries to do is more reactants are formed until equilibrium is restored. So it tries to take that product and it tries to break it down to reactants to restore the equilibrium. Actually, let me tell you, not the old equilibrium is exactly restored, but a new equilibrium is attained, whether it's at the same point, a little bit towards the right, a little bit towards the left, maybe far off towards the right, or maybe far off towards the left. So it really depends upon the change we're trying to make. I hope I'm making my points clear, right? Okay, let's take an example to make the whole thing easy. Ethanoic acid reacts with ethanol and forms ethyl ethanoate in water. Now, what is going to happen if we add any of the reactant? Let's say, as the book suggests, what would happen if we add more ethanol? So, ethanol is one of the reactants. If its concentration increases, according to the Shetland principle, it would try to oppose the change. If we increase the concentration of ethanol, it is going to, or the system is going to behave in such a way that it is going to decrease the concentration of ethanol. So some of the ethanol must be removed from the system. And the best way to do that is to react the ethanol with ethanoic acid in order to produce ethyl ethanate and water. That's what happens. When that happens, more of the product is formed. So writing the sentence that the position of equilibrium shifted towards right, ethanoic acid and ethyl ethanate reacted, sorry, and ethanol reacted to form ethyl ethanate and water would be the right thing. So it's pretty easy. Add any of these, the reaction moves forward. Okay. Add these, the reaction is going to move reverse. In the similar way, if we remove these, the reaction would be forward. And if I remove this, the reaction is going to be reversed. So that's how it works. The next example is the in the book says, what if we add more water? Now, what is the product? If the concentration of product is increased, the system would try to oppose the change as much as it can, so the position of equilibrium shifts to the left. It would try to consume water, it would try to react water with ethyl ethanoate, break some of it down back into ethanol and ethanoic acid, attaining a new equilibrium. So if we look at the next example, which says, what if we remove some water? So can any one of you tell me what happens when we remove some water? Remember, we're taking out a product. Yes, anything in mind? Nothing? Okay, it's going to be extremely simple. If we're going to remove some water, if the product is removed, the reaction is going to move into the forward direction, or the position of equilibrium will shift to right to form more water. Since we consumed water, it would form more water. The system is going to behave exactly the opposite of what happened during this change or during this factor getting implied. The same thing is mentioned over here, and the position of natural effect of the change in concentration affects the position of equilibrium in the formation of stalactites and stalagmites. And these are these rocks. They're formed due to the result of water passing through rocks containing calcium carbonate. The solution running through these rocks contain water, dissolved carbon dioxide, and calcium hydrogen carbonate. That's the reaction. And since it's a reversible reaction, the reaction may go forward or may go backward as per the scenario, as per the condition. Okay. For example, let's take a look at the practical activity 8.1 involving iodine, acid, and an alkali. Now, iodine dissolves in aqueous potassium iodide. We call this iodine solution. Iodine is also soluble in aqueous sodium hydroxide. In this activity, you will see to reverse the reaction by changing the concentration of acid or alkali. Now, you're going to need two test tubes and dropping pipette for this experiment. Procedure is you use a dropping pipette, put 1 centimeter depth of iodine solution in two separate test tubes. To the first one, you add dilute sulfuric acid and record any observations. The second one, you add dilute sodium hydroxide, record any observations. To the first test tube, I add sodium hydroxide until it is in excess, record the observations. To the second, add sulfuric acid until it is in excess, record the observations. How do you know that the reaction is reversible? Now explain in the results in terms of H positive ions of the acid and OH negative ions from the alkali. So of course, since we have added a little bit of an acid and to the same test tube, we added a huge amount of alkali, or vice versa. We have added to the second test tube a little amount of alkali and a huge amount of acid afterwards. So what is going to happen to this? I think you can easily tell us, right? You don't have the equation over here. Just a minute. Yeah, for this one, the equation is not written exactly. We just had these words. Okay, so you can always try this one out on your own. Next up is the effect of pressure on the position of equilibrium. But before I move any further,